Good evening. That was a photograph I took from the end of Bill a few years ago during a partial eclipse of the sun. But it was only a partial eclipse, which is not particularly spectacular. And I've just come back from the Philippine Islands where I've been seeing a total solar eclipse. And I'll say more about that later on. But you know, the sun is a fascinating body. It's our nearest star, and by studying the sun, we can learn more about the other stars also. And this is a good time to do it, because the sun is just starting to wake up, so to speak. It's past the minimum of its solar cycle, and we're starting to see sunspots again. Now, if you want to look at sunspots, you can do so, but I say again, please don't look straight at the sun through any telescope or any pair of binoculars, even if you use a dark filter. It simply isn't safe, and you'll blind yourself. If you want to see sunspots, use your telescope as a projector. Turn the telescope toward the sun, and then put the sun's image onto a screen held or fastened behind the eyepiece. And that's the way to do it. And that way, you will see any sunspots that may be around. And there have been some in the last few days. And here are 3 drawings I've made quite recently, in fact, from April the 2nd to the 6th, and they show dark spots on the sun's surface. And as you can see, from one day to another, those spots seem to move across the disk because they're being carried around by the sun's rotation. And that's a regular feature of sunspots. Now, they look dark. In fact, they're not. If you could see a sunspot shining on its own, the surface brilliancy would be greater than that of an arc lamp. Well, I'm afraid I can't move a spot away from the sun, but I can do the next best thing, and I can show you a representation. So here is a representation of the sun, and there are what seem to be dark sunspots. But without altering the brilliancy of those spots, I'm going to shift them off the sun's disk, and you'll see they start to glow brightly. And in fact, they appear dark only by contrast. The main surface or photosphere of the sun is something like 6,000 degrees centigrade, and the spots are 2,000 degrees cooler than that, which is why they appear dark. Now, what exactly is the sun? Well, it's a star, a globe of gas, 865,000 miles across, 93 million miles away from us, and shining not because it's burning, but because of nuclear reactions going on inside it. And every second of time, the sun is losing 4 million tons in mass. But please don't worry, there's plenty left, and the sun won't change in the long term for many thousands of millions of years yet. But of course, the spots do shift and change. At this stage, I'm delighted to welcome once again Iain Nicolson. Iain, what exactly are sunspots, and how do they behave?
Well, as you said, they're basically regions on the sun's surface, patches which are cooler than the rest of their surroundings and appear dark by contrast. You do find single sunspots sometimes, but they tend normally to occur in pairs or complicated groups, like the particularly large one that was seen in 1947 that we can see in this representation. Individual spots range in size from a few thousand kilometers up to groups like this that are more than 100,000 kilometers long. Now, the central part of the sunspot, 2,000 degrees cooler, is the darkest part called the umbra, and that's usually surrounded by a less dark region called the penumbra. And again, looking at a blow-up of this 1947 sunspot, we can see the kind of complicated detail of mixtures of umbra and penumbra that we tend to find. But sunspots are regions of concentrated magnetic fields. The strength of the magnetic fields in sunspots are about 10,000 times stronger than the magnetic field at the surface of the Earth. Of course, how do we know that there are strong magnetic fields there? And the answer lies in analyzing the sun's spectrum. As you know, if we pass sunlight through a prism or a spectroscope, we get the familiar rainbow band of colors, ranging from red through to blue and violet. But in the spectrum of the sun, we also have, superimposed on that, a pattern of dark lines. And these dark lines are produced by the atoms in the outer layers of the sun absorbing light from below. Each chemical element produces its own characteristic pattern of lines, and therefore we can identify what elements are present in the sun by looking at those lines. But we can extract a great deal more from the spectrum as well. In particular, we can use it to measure magnetic fields. If we have a look at an image of a sunspot and we examine that with a spectroscope, in the right-hand image here you can see an ordinary photograph of the sun. There's a big sunspot in the middle, and the thin dark line running down the middle of it shows the part of the sun that we're looking at with the spectroscope. So we start looking at ordinary photosphere, we cut across the sunspot and back to the ordinary surface again. Now if you looked at the left-hand image, the vertical lines are the dark absorption lines in the spectrum, and you'll notice that where those lines cross the region of the sunspot, a single line, especially that one in the middle, appears as a triple line. And this is the effect of a magnetic field on the light that's being emitted from the sunspot. By measuring the separation of those three lines and their strengths, we can measure the strength of the magnetic field and whether it's a north or a south pole. So that's how we know that we've got magnetic fields in the sun. Now, there is a device called a magnetograph which allows us to produce images of the sun's surface, showing us where the various bits of north and south magnetic polarity are. For example, if we look at the region of a complex sunspot, then we can see, as in this image here, the yellow areas correspond to north magnetic polarity and the dark blue areas to south magnetic polarity. And you can see clearly there how the different regions of north and south polarity exist in a sunspot group. This effect is called the Zeeman effect, incidentally. Now, if we look at pairs of sunspots, we find they behave rather like a bar magnet. So one sunspot will be a north magnetic pole, and its neighbour will behave like a south magnetic pole. It's very much as if you had a bar magnet sitting under the sun's surface between the sunspots. Now, of course, we don't actually have bar magnets floating around under the sun, but a sunspot pair is a region where a magnetic line of force loops out through the surface, coming out of one sunspot and popping back in through the other, giving the observed polarity pattern. Well, if we look now at the whole sun, we can get an impression of what this polarity pattern means. If we look at an ordinary image of the sun, then you can see a number of sunspots. There's a nice group up on the top right-hand side there, and some more down center left of the image. If we now merge that with a magnetograph, you can see quite clearly that the sunspot regions correspond with areas of concentrated magnetic field, the dark blue south magnetic polarity and the whitish colored north magnetic polarity. And this picks out a magnetic polarity pattern, which is a feature of the sun. If we look at the sunspot pairs in the northern hemisphere, then you can see the leading sunspot, that's the right-hand one, in each pair has a north magnetic polarity. Whereas if we look in the southern hemisphere, the sunspot pairs there, the leading sunspot, the right-hand one in each pair, has a south magnetic polarity. And that polarity pattern seems to be an underlying feature of the whole of solar activity.
Yes, but what concentrates the sun's magnetic field into these localized regions where sunspots appear?
Well, it all seems to be basically to do with convection. We're all familiar with the idea of convection, where hot bubbles rise in cooking pots when we're boiling the soup, or hot currents of air rise. And the same sort of things happening in the outer layers of the sun to produce something called granulation. And we can see that clearly here. The bright patches represent columns or bubbles of hot gas rising to the surface. The dark spaces between represent cooler gas descending into the interior. Now, the granules are circulating bubbles of gas about 1,000, 2,000 kilometers in size. But we think there are larger scale circulation patterns too, supergranules, perhaps 30,000 kilometers across, and very possibly hypergranules or giant cells, which dredge up hot material from perhaps as far down as 200,000 kilometers below the sun's surface. In fact, if we could take a slice through the sun's surface into the interior, we think it would look very much like this. Right in the center, there's the hot, dense core where the nuclear energy is being generated. That's surrounded by a region called the radiative zone, where energy in the form of photons, little bits of light energy, are struggling out towards the surface. And then beyond that, in turn, taking up the last 30% of the sun's radius, is the so-called convective zone, where this pattern of circulation is going on. Well, we think that what happens is that these powerful circulating currents of gas push together the magnetic lines of force, concentrate them in bunches or tubes, and these tubes float to the surface, and where they penetrate the surface, then we get a pair of sunspots forming. As it continues to spread out, the sunspot group grows and expands, and then finally the whole magnetic field dissipates and the sunspot disappears.
Well, now for the $64,000 question. What about the 11-year solar cycle?
Well, indeed, the number of sunspots increases and decreases over roughly an 11-year cycle, reaching a peak of activity once every 11 years. It reached the last minimum back in 1986, so as you said earlier, we're just beginning to expand from that.
Yes, indeed.
Now, here's a picture of the sunspot round about minimum activity, and there are practically no spots to be seen. Whereas if we look round about the time of a sunspot maximum, then you can see it's peppered with large, complex groups. We can also see, if we look back, say, over the last 60 or 70 years, how the numbers of sunspots have increased in this and decreased in this graph. As you can see, every 11 years there's a peak of activity, but successive peaks are not necessarily as active as the ones which preceded it. Now, in addition to the sunspot numbers coming and going, the locations where we find them on the sun's surface change as well. By and large, at the beginning of a cycle, a few sunspots begin to appear in a couple of belts, roughly 30 or 40 degrees either side of the sun's equator. Then as the cycle progresses, more spots appear, but the zone where they appear progressively shifts closer to the sun's equator. Round about the maximum of activity, the spots are concentrated 15 degrees either side of the equator. Then as the cycle progresses and the numbers diminish, they get yet closer to the equator until by the end of the cycle you've got a few spots of the old cycle down near the equator, just as the first ones of the new cycle are beginning to appear at higher latitudes. The third thing about this cycle is that the whole magnetic polarity pattern reverses at the end of one 11-year cycle. So if in the first 11-year cycle, as we can see here, the leading sunspot of each pair in the northern hemisphere was a north pole, and the leading sunspot in the southern hemisphere was a south pole, in the following cycle the whole thing changes, and the leading spot in the northern hemisphere is now a south pole, and the leading spot in the southern hemisphere is now a north pole. It's as if the entire magnetic polarity pattern of the sun reversed at the end of every 11-year cycle. And that reversal of magnetic activity does seem to be a fundamental feature of the sun's magnetic activity. Indeed, we can look at how the magnetic activity changes if we look at another couple of magnetograms. The one on the right shows the sun at a period of very high activity, where you can clearly see the concentrated magnetic fields in two belts north and south of the equator. The one on the left is the quiet sun, where there's no obvious pattern of magnetic polarities at all.
I've always been fascinated by the solar cycle. Iain, how do you think it operates?
Well, there's no clear answer to that, and we certainly don't have the answer to it yet. But one theory that's been quite popular for the last 25 years ago, originated by Horace Babcock, ties the whole thing into the differential rotation of the sun, the fact that the sun's equator revolves round in a shorter period of time than the area near the poles. And the Babcock theory suggests that if we think of a magnetic line of force, say, popping into the sun at the North Pole and skirting around under the sun's surface and re-emerging out of the South Pole, then as the sun rotates, due to this differential rotation, the line of force gets stretched. The equator pulls ahead of the pole, and after it's wrapped itself round a few times, then it's completely distorted round the sun, as you see here, and that distortion, that winding up of the field, concentrates it at the latitudes where sunspots appear. And so we can see these loops of concentrated magnetic force emerging and re-going back into the sun's surface. And you can see, looking at the loop in the northern hemisphere, that the line of force goes in to the leading spot, whereas in the southern hemisphere it comes out of the leading spot, giving us naturally that polarity pattern. And then finally the spots progress to near the equator, the sunspot magnetic fields dissipate, and you're back to the start of the next cycle with the opposite polarity. Very neat in many ways, but it certainly doesn't answer all the questions.
As you say, it's very neat, and for a long time it was really the only theory. But there's a new one now.
Yes, there's a very interesting idea which again ties the whole thing into convection. It's an idea suggested by Snodgrass and Wilson in the United States quite recently. The basic notion is that huge convective cells originate at the poles of the sun. And if we look at just at one quadrant of the sun, we can see that there are perhaps 4 of these giant cells in each hemisphere of the sun's surface. Now you can see the way that the convection's circulating by looking at the arrows. And gradually these circulating cells progress down towards the equator, taking about 22 years to get there. And where 2 converging downward flows meet, there you find a sunspot forming. That concentrates the magnetic fields. And so as the rolls move down towards the equator, the sunspot area moves down as well. By the time the spots reach the equator, the next pair of downward going rolls has reached 30 degrees latitude and produces another cycle of sunspots descending towards the equator. And this thing repeats over an 11-year pattern, producing opposite polarities with each successive pair of rolls. So again, a rather nice idea, but it's much too early yet to say if it's going to be the new accepted view of how sunspots are produced.
Well, there are plenty of new ideas coming along, and another recent discovery is, of course, the revelation that the sun is actually oscillating or vibrating, wobbling, rather like a jelly.
Yes, this is an interesting one. The whole surface of the sun is vibrating up and down, going up in some areas, down in adjacent areas. And really the best way to represent this is to think of it as if the sun was oscillating in the same sort of way as the surface of a drum. And I think we can illustrate that here with a bit of luck with this timpani. If I give it a good bash or two, just watch what happens. You can see quite clearly there how the whole surface of the sun's vibrating up and down in localized regions. These vibrations, most of them take periods of about 5 minutes, so they're quite rapid movements on something as big as the sun. Now basically these oscillations are due to something rather like seismic waves in the earth. Rather essentially they're just sound waves. And what happens is if a sound wave is moving down in towards the sun's interior, it's moving into a region where the temperature is higher, and then it moves faster. That causes the path of the sound wave to bend, and it loops up back to the surface again. When it hits the surface, it bounces off back into the deep interior once more, accelerates, bends up, hits the surface, back down inside again. And if it manages to go around in a complete set of loops, so it meets up with itself, so to speak, then it produces a pattern of standing waves at each point where it meets the surface. And the sun's surface oscillates up and down at those points until, after a while, other disturbances cancel it out and the vibration disappears. So in the sun's interior, all the while, there are all kinds of vibrations occurring. Of course, some of them don't go down so deep, and they meet the surface more frequently. So we can see here's a pattern of 6 oscillations. There are literally thousands of these oscillations going on, and the intermingling of them is what produces the observed vibration of the surface. Now we can use that information, analyze these oscillations to get information about the conditions inside the sun in much the same sort of way as geophysicists study the interior of the Earth by seismic waves from earthquakes and other natural phenomena. And this can reveal a variety of things. It can reveal how the temperature increases as you go down inside the sun. It can show whether the sun's spinning faster inside than it is at the surface, and a variety of other things about the sun's structure. And already these measurements have revealed that the convective zone is deeper than astronomers previously thought, and contrary to what many astronomers thought, the interior of the sun, or deeper down in the sun, does not seem to be rotating faster than the surface layers.
And we still have that neutrino problem.
Yes, and it's just possible that oscillations might help us out on that one too. The solar neutrino problem, which we've covered before, of course, or you've covered before on this program, is essentially that neutrinos are ethereal little particles emitted in nuclear reactions in the solar interior, and we don't receive as many of them as we think we should. And by studying the oscillations, we can find out what the core and interior is really like, and perhaps get an answer to why we're not getting as many neutrinos as theory suggests.
So there's a lot to be learned. But you know, I always think the sun is at its most spectacular when it's totally eclipsed. Well, I mentioned eclipses at the start of the program, and I've just seen a total eclipse in the Philippine Islands. That happens when the moon goes in front of the sun and for a few minutes blots out the sun's bright face, and it really is a sight. I went to Talicut Island in the Philippines, and there are some pictures of the preparations, and as you can see, the sky then was cloudy, and it was cloudy right up to the last moment. In fact, 10 minutes before totality, rain started to fall, and we gave up hope. But then I'm delighted to say the sky cleared, and we did see the eclipse. And there's a photograph I took showing the inner corona and 2 red prominences, an even better one taken by Douglas Arnold that does show the corona in more detail. A certain amount of cloud was left, but not enough to worry us, and it really was a magnificent sight. Sadly, you won't see a total eclipse from England until the 11th of August 1999 from Cornwall, but I assure you that I'll be there with the Sky at Night program if I'm still around. Incidentally, before I go, the newsletter's ready, and if you want it, please send your stamped addressed envelope, as usual, to newsletter number 29, The Sky at Night, BBC TV, London W12 8QT, or if you like, look at CFAX 148. Ian, you know, the sun's waking up. I think it's fair to say we have a long way to go yet.
Yes, I think we know more, but we actually understand less than we did 20 years ago.
And the sun is a fascinating body. We'll wait and see what happens. And from Ian and myself, good night.